Assalamu alaikum and greetings, everyone. We are from Group 11. My name is Aisha. We have Mirza Nabil, Sharifa Nasibah, Tanta Yao, and one Nur Shaidatul Shazlina. We will be presenting regarding our semester's project on the plant design for sulfur oxides emission reduction of thermal oxidizer flue gas. Now let's get started. The outline for today's presentation will revolve on the process overview, the proposed waste treatment, cost analysis, and finally the conclusion recommendation. Now for the introduction. Firstly, we have to identify the problem statement, which in our case is to propose a solution to reduce or remove the sulfur oxides emission from an existing thermal oxidizer. This leads to our objectives, where we want to propose a design for a plant that complies with the Department of Environment rules and regulation. Number 1, we want to reduce the sulfur oxides emission from the flue gas. And number 2, we want to produce at least 2 value-added products. For our scope of study, we will focus on the routes to reduce the emission of sulfur oxides, and also we will conduct an economical analysis and finally explain regarding our waste treatment strategies. This table shows the air pollutant emission limit that we retrieved from the Environmental Quality Regulations 2014. We will now proceed with the process overview of our plant. I will explain the process by displaying the process flow diagram of our plant here. Firstly, we will have our ammonium hydroxide solvent that we will be using for both the sulfur dioxide and carbon dioxide absorption process. This will first enter the SO2 absorber, where the flue gas comes in from the thermal oxidizer. The absorber operates at 28 degrees Celsius and 911 kilopascal. The gas will be leaving the top of the column and it will enter the CO2 absorber. What's leaving the bottom of the column will be a mixture of SO2 and ammonia, which is ammonium sulfite, and it will enter a reactor to convert the ammonia sulfite into ammonium sulfate, which happens to be our value-added product. Now, the gas leaving the absorber, as mentioned just now, will enter the CO2 absorber unit to further separate the CO2 from the gas stream at a temperature of 25 degrees Celsius and 121 kilopascal with a conversion of 90%. The gas leaving this unit will be free of CO2 and SO2, and it will be enter a washer before it is sent to purging, as it has met the regulation limit. Now, the liquid stream that leaves the CO2 absorber will be ammonium hydroxide solvent that is rich in CO2. It will enter a stripping unit that operates at 91 degrees Celsius and 2790 kilopascal at a conversion of 60%. Now, the ammonium hydroxide solvent will be regenerated and recycled back for the absorption process, whereas the pure CO2 will enter the methanol reactor. At this reactor, carbon dioxide will enter at 210 degrees Celsius and a pressure of 7,900 kilopascal to form methanol and water. However, this stream will be a mixture of gas-liquid stream before it will enter a phase separator to separate the unreacted carbon dioxide and hydrogen with methanol and water. Now, the methanol and water that leaves the bottom of the separator will enter a distillation column. The methanol will be separated from the water by its boiling point, so now methanol will become our next value-added product from pure CO2. Now we will move on to the instrumentation and control, where I will give a brief overview on the process units in our plant along with the control objectives and the type of controller. The first unit is the cooler or heater, where we want to control the temperature by using a cascade controller, followed by a compressor, which we want to prevent the backflow by using an anti-surge integrated controller. The next unit is a two-phase separator, where we want to maintain the liquid level, the top pressure, and the temperature of the outlet by using a cascade controller. All three next unit uses a cascade controller. So the first one is a distillation column, where we want to maintain the top pressure, the top temperature, the level at the reboiler tray, and the pressure at the reboiler tray. Then we have a reactor to maintain the temperature as well as the differential pressure, and finally an absorber to control the pressure and as well as the level inside the absorber. So now I will display the PNID for ammonium sulfate production that uses the control strategy explained just now, followed by the PNID for methanol production. I will now pass the floor to Wanda Shaidatul Shazlina to explain regarding the waste treatment facilities.
Thank you, Aisha. Hi, I'm Shazlina. I will be presenting about the waste treatment facilities. The ultimate objective for the waste treatment is the protection of public health in a manner of environmental, economic, social, and political concerns. Generally, there are three forms of waste that will be produced from a chemical plant, which are solid, liquid, and gas. However, in the production of methanol and ammonium sulfate from flue gases, there are two types of waste produced, which are gas and liquid waste. These are the identified gas waste, which consists of the nitrogen, NMVOC, carbon dioxide, carbon monoxide, and ammonia, whereas for the liquid waste consists of the ammonia, ammonium bicarbonate, nitrogen, and also methanol. These discharge wastes have their own effects on environment and living things if they exceed the safe limits emission. Therefore, a proper waste treatment strategy needs to be proposed to treat these waste by reducing the emission limit prior to the environmental laws and regulation. Across the years, acts and regulations regarding the effluent and sewage discharge have been provided and enforced by the Malaysian government authorities such as DOE, NIOSH and also DOSH. So for the gas waste, Environmental Quality Clean Air Regulation 2014 has been referred and it applies to any premise used for any industrial or trade purpose, including burning of waste, potential to discharge air pollutant into the open air, and for any burning plant and equipment. And for the liquid waste, the Environmental Quality Sewage and Industrial Effluent Regulation 2009 has been referred to. Operating chemical plant or industries that produce waste must comply to this regulation to maintain the quality of environment in terms of air and water pollution. These are the proposed waste treatment facilities for the gaseous waste. The first method is the wet scrubber. Wet scrubber able to remove particles, unwanted gas from the exhaust stream. It can remove gas pollutants such as ammonia, chlorine, and also sulfur efficiently. Wet scrubber also has low capital cost and it requires a small space. Wet scrubber also able to neutralize corrosive gas and also dust. The next method is the bioscrubber. Bioscrubber is the combination of the gas scrubber and biological reactor. It can remove gas pollutants such as alcohol, odor, carboxylic acid, and esters, nitrogen compound efficiently. Bioscrubber also has a low operating cost and a better life cycle cost. The advantage of this bioscrubber is that it can remove 98% of hydrogen sulfide. In the bioscrubber, nutrients are needed to ensure the microbial biodegradation activity to happen. And for the liquid waste, these are the proposed waste treatment for the wastewater treatment plant. The first step is that the screening, which consists of the coarse and the fine. It is a physical treatment to remove large objects such as rags, paper, plastics, and metals to avoid operation problems. After the screening process, it will go through the API separator where it will separate the oil and suspended solids using specific gravity difference. In here, the suspended solid will settle to the bottom while the oil will rise up and get skimmed off to remove it. After the API separator, it will go through the equalization tank where it will collect the incoming raw effluent flowing at a wide fluctuating rate and will let it out at a steady flow rate. The advantages of the equalization tank is that it can control the pH of the system, it also can minimize the usage of the chemical, and equitank is said to be economically beneficial. So after the equalization tank, it will go through the activated sludge process. Activated sludge consists of two processes, which is the primary and the secondary. The primary process will remove matter that use up oxygen, remove odor, reduce volume, and kill disease-causing organisms. Materials that settle out from the primary sludge process need further treatment. Therefore, comes the secondary sludge, in which the extra microorganisms are to be treated. So, with the proposed waste treatment facilities, it is believed that the discharge of the liquid waste and the gas waste will reduce and minimize up until the safe limit as stated in the regulations that has been referred to, and it can be safely discharged to the environment. So I'll pass the floor to Tan and Nabil for the cost analysis part. Thank you.
Thank you, Shazlina. Assalamualaikum and a very good day. I am Mirza Muhammad Nabil Bek, and I'll be presenting the first part of cost analysis for our plant design project. These are the values that we used for our value-added products and raw materials. By assuming that the plant operates for 8,000 hours per year, we calculated the economic potential level 1, EP1. So our EP1 is RM 671.96 million per year. And then we calculated the economic potential level 2, which is basically EP1 minus total utility costs. We total the utility cost, which is comprised of the total cost of coolers, total cost of heaters, and total cost of compressors and pumps. We got the EP2, which is equal to RM 301.64 million per year. Note that this is calculated after heat integration, so a total of approximate RM 38 million per year can be saved after implementing heat integration. Now we proceed to the capital investment calculations. From this point onwards, a textbook written by Douglas in 1988 titled Conceptual Design of Chemical Processes is used as the main reference. So as listed in the table seen on the screen, this is the total purchasing cost of all equipment, which is comprised of sulfur dioxide absorber, carbon dioxide absorber, methanol reactor, carbon dioxide stripping column, and etc. etc. So the total purchasing cost of equipment that is to be installed in our plant is RM 123,106,079.44 cents. So the total capital investment can be calculated by adding up the fixed capital investment with working capital and startup costs, and the total capital investment for our plant design project is RM 746,502,955.10 cents. And then we calculate the operating costs or OPEX. So these are the three main operating costs that we calculated for our plant design. So those three are variable operating costs, fixed operating costs, and general expenses. The values and details are as per seen in the table on the screen. So the total operating cost for our plant design project is RM 846,428,434.27 per year. So now I'll pass it over to Tan Tai Yao to continue with the second part for cost analysis.
Thank you, Nabil. Hi, my name is Tantaya and I'll be presenting the second part of the cost analysis, which covers the total revenue, gross income, economic potential level 3, EP3, and also the profitability analysis. As mentioned, the plant is operating for 8,000 hours per year. Therefore, the total revenue is calculated to be 1.1 billion ringgit per year. After taking into account for the OPEX determined earlier, the gross income of the plant is 268 million ringgit per year. Moving on to the project economic evaluation, the EP3 is the subtraction of analyzed cost of equipment from the EP2, which is calculated to be 293 million ringgit per year. Next, the profitability analysis of the plant is carried out and it consists of these 6 aspects, which I will discuss after this. Before that, a few assumptions have been made to ease the analysis. For instance, the plant life is 15 years, the plant is operating for 8,000 hours per year. The minimum attractive rate of return MARR for this project is assumed to be 10%, and the plant construction period is 3 years before the production begins, and therefore the TCI will be focusing on the first 3 years. For the details of the total capital investment, 30% of it is invested in design and engineering aspect in the first year, while 60% of it is invested in the procurement and construction in the second year, and the remaining 10% is invested in the remaining construction in the 10th year. The breakdown of the values is shown in the table. Next, the depreciation value is calculated using the equation as shown, and it is determined to be 48 million ringgit per year. Moving on to the payback period, the TCI can be recovered by the net profit of the plant every year after deducting the depreciation value and the income tax of 25%. Based on the graph, it is observed that the payback period is determined at the 5th year, where the cumulative cash flow is positive. Besides that, the rate of return of the plant is calculated using the equation as shown, and it is determined to be 15.39%, which is higher than the assumed MAR of 10%. From there, the plant is proven to be economically feasible. Moving on to the net present worth, it is calculated using the equation as shown. Based on the table, we can see that the 15 MPW is a positive value, and therefore the project is economically feasible. Last but not least, an internal rate of return of 20.76% is obtained in determining the discounted cash flow rate of return, which is greater than the assumed MAR 10%. Besides that, a positive value of 15 DCFRR is obtained as well. Therefore, we can conclude that the plant design is economically feasible. That's all from me. I would like to pass the floor to Siba for the conclusion.
Thank you. To conclude our project, we have successfully achieved our main objective, which is to reduce SOx emission while complying to CAR 2014 requirement, which correlates the relationship between human and also environment. We also managed to design a proper waste treatment system that has been discussed earlier by Shazlina according to environmental laws. In addition, we also managed to achieve our value-added product production such as methanol production by 40% and also ammonium sulfate production by 13%.
Next, the significance of performing cost estimation is to determine the plant feasibility. The plant is expected to operate for 8,000 days per annum. We also conduct plant investment estimation and production costs that are required, which is CapEx, OpEx, estimation of total revenue, and profitability analysis that were discussed before by Nabil and Tan. The payback period is determined at the 5th year, where the cumulative cash flow of the plant is positive. In addition, we managed to develop HAZOP studies to ensure the safety of our plant. HAZOP is a structured brainstorming technique to identify hazards and used to evaluate the significance of deviation from the normal design intention of equipment in our plant. Last but not least, the feasibility of building our flue gas treating plants were analyzed thoroughly to select the best location based on energy, availability market, and transportation facilities, which is Thursday. That's all from us. Thank you.